All right. So, let's start the night. We can just do it 2D because we don't need to prove anything. We know that we can do the 3D stuff, so we can do the math in 2D because it's a lot easier to see. And then once it works, we can do it in 3D. So I'm just going to stick with the old-fashioned 2D stuff for a minute, so we can talk about the fundamentals of the math, and then I think I'll even step into Octave and write out some matrices so you can see what's going on. Okay, so the first thing is, in order to do these transformations, they're using linear algebra. They're doing 4x4 matrix multiplications, and I'm going to show you why you shouldn't do it by hand, because the graphics card basically does this in hardware really, really fast. So you should just let them do their thing. But I'm not going to demonstrate that in code. You're just going to take my word for it. I'll just show you what they can do really fast. Okay, so let's start out by drawing a rectangle. How about 0, 0, 100, 100? Okay, so that should be fairly obvious. We did this on the first night. Let's see. Okay, so there's your rectangle. Okay, so the rectangle is the top left of the screen, right? Now, we've said that if you wanted to move it, you could translate by, let's say 200, 200, and you're moving the origin. So now, basically, this is what you're adding to every x, and this is what you're adding to every y. So if you do that, sure enough, the thing moves over 200 and down 200, and it's there, right? So you might ask, well, why do I have to do this? Why don't I just do it by hand, right? Why don't I just put the 200 in myself? So in OpenGL, the answer is because you can't, right? That they just don't provide you with a way to make a sphere at a particular location. I mean, the API that they're providing you just a sphere, right? So you have no choice but to translate. But more to the point, I want to show you how we rotate something around something else. So what's involved with the math, right? So the reason we don't do this, we don't manually do it, is because it's just not a great idea. We'll get high speed from the hardware if we let them do it. But also, for the math, it's really nice if we constantly think about everything at the origin. So let's see what we can do. All right, how about this? I'll set up the origin as width over 2, height over 2. We've got our 800 by 800 playing field. Okay, and let me do a circle. So circle 0, 0, and radius 100. Let's see if that works. Okay, so we got a circle at the center of the screen. I think that's right. I don't think... Is that this? I can't tell if it's the center of the circle that's in the middle or the top left. I honestly don't know. I think it's the center, but... Alright, if I'm wrong, we'll see. Okay, so... If I say that the origin is now width over 2, height over 2, I think it's pretty obvious that anything I do is with respect to that origin. So, like if I say scale the circle by 2, you expect the circle to get twice as big, but to stay put because it's centered on 0, 0. So, yeah, it works, right? It just gets bigger equally in all directions. But if I did a rectangle, that would not be true. Because the rectangle is definitely located, the top left corner of the rectangle is at 0, 0. So, oops, sorry, I gotta have 100, 100, right? So, now you can see the top left corner is in the middle of the window. And if I scale it by 2, you'll see that the top left corner is still at 0, 0, right? Because 0 times 2 is still 0. So, but everything got bigger, but it got bigger asymmetrically, right? Because it was already asymmetric. So this kind of points to the math problem that you have if you want to like orbit something, right? If you want to rotate around something, you have to make it the origin. So what I'm going to do, I'll just use circle because it's like nice and symmetric, but what I'm going to do now is let's try to make this circle orbit someplace, right? Now, in order for you to see what it's orbiting, let's draw it. So let's see. Let's say we're going to draw the sun, right? Let's draw a circle which is yellow somewhere on the screen, and then let's make this circle orbit around that circle so you could see it happen. And we're going to do the same thing in 3D. It's just easier to visualize in 2D. So how can I draw a circle? Give me some place on the screen, and how can I draw a yellow circle? What do I do? Fill. What do I say? How do you make yellow? Anyone? You're saying no red, green and blue? Yeah, I'm not so good, but I'll take your word for it. You know what? If it's not the right color, I won't hold you. I won't blame you too much. All right. So we're going to make a circle now. Now, where are we going to put this? Where are we going to put the sun? Let's just decide where the center of the solar system is, right? So we're going to say float CX. So the center of our solar system. Let's just make a place. Don't make it the center so you could see it, right? I want you to see our circle orbiting something. What do we do? Give me a spot here. Anybody? How about 250 CY equals 100? All right, so basically if the center is 0, 0, we're somewhere to the right of center and somewhere down at the moment from center because we're still upside down coordinate system. You know what, let's fix the coordinate system too. Anybody remember how do you fix the coordinate system? How do you scale it to make it right side up? Yeah, so x, just x leave alone. So remember, x is 1, and there you go, right? Okay, this is only, by the way, this is only in processing you have to do this. In OpenGL, the default is right to begin with, right? In processing, it's kind of like the web way. Integers are counting downward down the page. So, in physics, OpenGL is kind of like physics, right? Okay, so there's our scale, and we're going to draw the circle. Okay, so we're going to draw the circle at CX, CY with a radius of 100. All right, and then we're going to fill with, all right, 255, right? So just a white circle. Let's see what we got. No, okay, green plus blue is like cyan, turquoise kind of color, right? So that's not it. I think it's red and green, if I'm not mistaken. So red, green, no blue, because red and blue make pink, or a little, RGB. So right? There's our sun, right? Okay, so we want to make the white circle orbit the yellow circle, right? Now, of course, we could do all the math ourselves by hand, but I'm here to show you why you don't want to, because this stuff is infinitely faster on the graphics card. Your GPU, I'm desperately trying to learn it now to teach it in the fall. So I'm seeing just what the power is of the graphics card, and oh my God, there's thousands of CPUs on your graphics card. So it is potentially easily 1,000 times faster than your CPU if you could only use it right. And for graphics, it's the perfect parallel problem, right? All these dots on the screen can be drawn in parallel. So the GPU is perfectly suited for making your graphics stuff way fast. So if you have 1,000,000 points, yes, you have to do a matrix operation, as you're going to see, to do a transformation, but it can do that on 4,000 processors, so there's no way you're going to do it faster than that. All right, so this is what we're going to do. We are, of course, going to draw. No, we're always going to draw it at. I want to say 0, 0. All right, let's do it this way. How are we going to draw the sun? Let's start by saying we will translate CX, CY. So instead of saying we're going to draw the sun at CX, CY, we're going to translate by CX, CY, and now that is the location of the sun. So 0, 0 is the sun. And now our job is going to be to transform the Earth around the sun. So let's say, or well, I don't know if this is the Earth. It's some planet going around a star, right? Okay, and I'll just make it like 10, so it's obviously smaller. So you, all right. So suppose we're going to have the, oh, you know what? I'm going to make the window a little bigger so we don't go off the edge. Not that it matters. Okay, so suppose we have this white planet circling the yellow star at a distance of 100. Now, if it's a distance of 100, you know, I think this is diameter, not radius. Yeah, I think that's 50 dots. Well, if it was a distance of the radius, then you would actually see the two overlapping. In fact, let me do that. All right, so I'm just going to first translate by 50, 0. So if I'm drawing the sun right here, if 0, 0 is the center of this thing, and if I go by 50, 0, Earth should be drawn right there. So let's see what happens. Yeah, and there it is, right? Little teeny planet right at the surface of the sun. So it's melting. All right, so now I'll translate so it's a little bit further away. It's 100, and I'll make it a little bit bigger, make it 20, just so you can see it better. Okay, so now we have something that looks like a cartoon-like, you know, solar system. All right, so we want the Earth to rotate around the sun, right? So notice the first thing I did, I translated by 100. So let me call this the orbital radius. It's better to have names for these things, right? So we could say final float orbital radius equals 100. All right. And but we don't always want it to be, you know, to the right of the sun. We want it to go around, right? So what we have to do is rotate, right? So we're going to say rotate by A. Okay, so remember, we said this is why I'm telling you the way you work in OpenGL. We translated so that the sun was the center of our universe, right? Our coordinate system was based on the sun. So instead of planting the sun at an arbitrary location, we defined that location as 0. So now everything's with respect to the sun. So I can leave it in that frame of reference. Okay, so let's call this one float orbit angle. So this is the angle as Earth is going to go around the sun, right? And right now you can't see anything because you can't see the orientation because it's a circle. So, you know, I'm going to make it a square, actually. I'm going to have a square planet. And the reason is I want you to see when I rotate it, actually, you know, when it's getting messed up. So, all right, I'm even going to make it bigger because I really want you to see this better. All right, but oh shoot, I don't want it to be the top left corner, right? I want it to be centered because otherwise it's going to be a little bit weird. So just give me a second. Oh, I know how to do this. Let's get help. Let's go to reference. All right. Rectangle. Rectangle. Okay, rect mode. They don't let me click on that? That's annoying. Back up. Rect mode. Rect mode center. Okay. So we're just going to call this 1 time so rectangles are centered. All right. I've got to save it. Right. Okay, so this is S09 2D solar system. Okay. Okay, so this is not A, this is called orbit angle. We are going to start orbit angle at 0, and we're going to just increment it every time. Now, we don't care about scaling of time or anything, like we don't know whose solar system this is, how fast it goes, so we're just going to say orbit angle plus equals, you know, some nice small number like that, and it'll go around the surface. Alright, so let's see what we got now. So I rotate the orbit angle and I translate it by that orbital angle. Alright, this is going to work. Alright, now you can see that as the square is going around the star, it's always keeping one side to the star, because when you rotate it in its orbit, you're also rotating it in space. That's what I ended with last time. So we need to go over the math of how we make that not happen. So first of all, background 0, so we got space. Okay, so we rotate the orbit angle so that, oh, let me turn on my video so you can see, I can gesture at you. Hello everybody. So here's the sun, right? Here's my planet. In order to draw the planet in a new place, I rotate my frame of reference. So now this is X, and later on then this is X, then this is X. So I'm rotating everything, right? So I'm not only rotating where I'm going to draw it, I'm rotating everything, including what I'm drawing. So, and I showed you that in my notes. So by rotating the orbit angle and then translating, then whatever we draw is in fact rotated. So sure enough, right? Okay, so now what we can do to unrotate that is rotate by the exact opposite once you're there. So you rotate your frame of reference, then go there, then unrotate, and now it should stay the same. You know, it may not be 3D, but I really like this thing. My cartoon, I'm gonna have to definitely keep this. This is really cool. Like the geometry solar system will be like triangles and stars, and this would be kind of funny. I could make the main star an actual 5-pointed star or something. That would be fun. All right, but it's a lot of work because none of those things are done for you. Okay, so now, so how would you go about doing a second one, right? So if you were now to say, okay, I want to draw a second, so let's draw let's do Mars, the small red rectangle. So red 0, 0. I guess Mars isn't quite so bright, so I could make it like 180 red and a little bit of, I'm just making that up, I don't know what color it is exactly, but it'll be red-ish. And now I draw a rectangle 0, 0, 20, 20. Alright, now the problem is it's going to draw it in exactly the same place as the other one, right? That's not very nice. That's not what we want, right? We want Mars to be a different body. So what we got to do is, first of all, so now we should rename this, right? This is orbit angle Earth. This is orbit angle Mars. So what we want to do is orbit angle Earth goes like this. Orbit angle Earth, right? And now we want to do Mars. We fill it. Sorry, this is all. So this stuff was all the Earth, right? So it's this bunch of lines. So we want to do exactly the same thing for Mars, right? It makes a lot of sense. The problem is it's not so easy because, all right, I just pushed that. All right, that's all the stuff for Earth that I'm copying. The problem is, oh, so this is, sorry, orbit angle Earth. The problem is that we've already set our transformation for Earth. So now anything we do to Mars will be on top of whatever we did. So either we'd have to undo everything we just did, which is a nightmare, or we need to remember what we did and, how do I say this? Remember what we did, remember where we were before we did all this stuff. Now, in 3D, I can tell you what it is. I've never tried this before, but I'm going to just try it in 2D to see if it works. It's called push matrix in old OpenGL, and they use this stuff. They're using old OpenGL. Push matrix and pop matrix. So what you're saying is, this is like the commercial, what happens in Vegas stays in Vegas. When you say push matrix, whatever you do to the transformation matrix in here, when you say pop, it's all gone, and now you can do it again. So the only problem here is I'm not sure that that thing is supported in 2D. We're about to find out. Okay, so I set the color, right? I'll say okay, so what should I put for the comments here? Rotate Earth to correct place in orbit. All right, so there's two things I think we have to do here. First of all, I'm just going to try to show you how to do two planets that are independent of each other. Secondly, we're going to try to make Earth spin correctly. So, all right, well, not correctly because it's just a rectangle. So if we want Earth to rotate in 2 dimensions, we're just going to say orbit angle Earth and rotate Earth. Okay. So you now notice these two numbers they're going to both start at 0 because I'm just being arbitrary here, but I can make them increase at whatever rate I want to. So every time we refresh the screen, we're going to move the Earth by about 1/100th of a radian. I don't know what that is right? It's like 57 degrees divided by 100, so 0.5 degrees. So about 720 times to go around the circle. So we can make it spin faster. Rotate Earth plus equal 0.066. All right, so this is how fast it's spinning. Now, in actual fact, this should not be some kind of like mystery, right? We know that the Earth takes a year to go around its orbit, and in a year it is approximately, not exactly, 365 days, right? So I could, if I really wanted to, I could just say, all right, let's do it like this. Let's just call this DA, delta angle, right? We'll pick whatever the hell we want to do for delta angle based on our animation. So final float delta angle equals, all right, let's just take that as the base speed of our animation, right? So whatever that one is, I know that the rotation is about 365.25 times faster than that one. All right, so now so the point was this first thing didn't change the rotation of Earth, just put it in the right place. This second thing rotates it correctly for the day. But of course, I'm just making these numbers up. I mean, it's roughly right. It's a cartoony thing with a square, but it's roughly right. You can do it really right in 3D. We can like tilt the axis by 23.5 degrees and spin it and do the whole thing if you want to. All right, now to do Mars, we have to do exactly the same thing. So this becomes Mars. Okay, that's orbital radius Mars. Oops. So this is orbital radius Earth. Okay, so where's orbital radius? Orbital radius Earth equals 100. Orbital angle Earth is 0. Rotate Earth is 0. Orbital angle Mars. Float. Orbital radius Mars equals 200. So we're making Mars twice as far from the sun as the Earth. That's not true. I can make it like 160. That's a little more accurate in my cartoony world here. And orbit angle Mars and rotate Mars. Okay, now you notice that everybody's starting at 0, and they don't know, the planets aren't normally like lined up when you start a, but you know, you don't know where you're starting. I just make up the simulation, so this is fine. But obviously they start lined up, which is a little weird. If you want to do a really good job, you're going to start them at random points, or if you really want to do a good job, you can look up the positions in a database. They have online stuff, of course, but it's hard. Okay, so we have orbit angle Mars, orbital radius Mars, orbit angle Mars, orbit angle Mars plus equals, all right. So now, okay, if we define that our delta angle is what the Earth is doing, then Mars obviously goes slower than the Earth. I don't know what the ratio is, but I think the Martian year is like it's like close to 2 Earth years. It's been a while since I read The Martian, so you could check me up on it. So I'm just going to say delta angle times, like, I don't know, 0.55. It's just a cartoon, right? Okay, but you, again, so we're doing everything, we really should do is to get the actual physics numbers in, put them in the simulation. And what I want to encourage you is, if you really want to do this right, and for those of you who are like C++ or Java aficionados, you can write an object which contains all this information. You write one class called a planet or a moon or a body, make it go, and then make everything else work. You could just write this once and just load it up with numbers. And I've always wanted to do it, never had the time to do it. So I'm like dying to have a student do it so I can like show this off as an example. Your name will be up in lights if you can do it. All right, orbit angle Mars and rotate Mars plus equals, all right, I have no idea what the Martian day is like, but it's slightly longer than Earth's. So if we're 365, let's call it 340. Close enough. All right, let's see what we got. Okay, so the Earth is spinning wildly. Okay, I think pop matrix isn't working worth a damn. Push matrix, pop matrix. All right, so unfortunately for me, I don't know how to do this. Let me just see if there's a way to do it in 2D. Because this is so nice to convey the stuff, but if I can't duplicate it, we'll just do it in 3D. It's not such a big deal. But processing, how to reset projection 2D. Well, they say it works. Okay, I could be doing something wrong. Alright, so they claim it works. So that's a good sign. Alright, so we are rotating by the Earth, translating, unrotating, and then rotating the Earth. And the Earth was in fact working correctly. It was spinning. And we draw the Earth, and it's in white. And then we increase the orbital angle. Okay, now that's not inside push matrix, pop matrix. That's just simply every time you draw it, you update the numbers. Okay, and then Mars we're drawing in red. Oh, whoops. I don't think I shouldn't need a push matrix here because I've got nothing to remember. By the end of the function, it's over, but I'll just be consistent. There's a white, so that's why. All right. Now, definitely don't draw it there. Draw it there. Okay, so let's look at what that does. There we go. Okay, so the only thing is that Mars is not rotating, so we have to. I obviously did something wrong. And you can see that what I don't like is that the Earth is going so fast you can't really see it. And this is the problem with cartoons, right? You're not gonna be able to make everything. You're gonna make everybody happy, right? If you want to see this, you got to slow it down. If you want to slow it down, then it's going to go very slowly around the sun. But too bad because that year takes a while, right? So I just have to make the whole thing slow if you want it to be to scale. So delta angle, we're going to just drop it by a factor of 10. All right. Now, why wasn't Mars rotating? We orbit angle of Mars, orbital radius, negative orbital angle. That worked. Oh. And then we never rotated by the rotate Mars. So there we go. Okay, so this code maybe. Alright, so hopefully those comments will help you understand this code later if you're looking back. Alright, so you notice they all start lined up, which is on the other side. Wait, why is it so fast? I was supposed to slow this thing down. I made delta angle 1/10 as big. It's still fast? Huh. Well, now it's slow enough, but now it's like painfully slow to go around the sun, so take your pick. Alright? See, I told you, you're not going to make everybody happy. Alright? Now it's, yeah, whatever. Okay, but there you go. So Earth is going faster around the sun, as you expect, because it's closer in. But there's no physics here, right? I haven't done a physics engine. All we've done is we've scaled everything. It's a clockwork, right? Everything's moving at the speed it should, and we just started at arbitrary locations. So after a while, it looks kind of realistic, but it's not realistic at all. Any questions? Ooh, yeah, but it's much harder. Let me think about it. Okay, so an elliptical orbit is, you've got two numbers, the major and the minor axis. All right, so the easy way would be if we don't try to rotate that, right? I'm thinking. All right, so first of all, this is a great question. first of all, that's something we're not going to be able to do with transformations, right? So the moment you do something that's not like the same every time, you know, you can do it in OpenGL nowadays because you could download whole programs to the GPU, but you're not going to be just multiplying some matrix. You're now going to be writing code. So what we want to do is every time you do it, where is it? Translate. This is not a constant anymore. What you're going to do now is you're going to calculate it, right? I love it. Great question. All right. Now, without loss of generality, does everyone accept the fact that I can just define the sun at 0, 0 so that we're in the center of the screen, so I don't have to worry about the fact that we're off the edge? Because I'm going to make the orbits a lot bigger, and because I'm going to make the Earth's elliptical. So, just to prove it to you, I'll go like 100, but I want to leave that 1,000. I want to have plenty of room to swing here. Okay, so what we're going to do is I am not going to make the orbital radius for Earth final. I'm going to calculate it now. So I'm only going to make Earth elliptical. Yeah, you're anticipating all the things I want to do. I want somebody to write me a class in C++ or Java and make this damn thing work and do some gorgeous solar system, like the whole thing. Orbital radius Earth equals. All right, wait a minute. So, well, we will have a final. Let's say final float. Let's call this Earth 0 equals 200, and Earth 1 equals 300. So I'm purposely making it ridiculously elliptical, right? The Earth's orbit is not that eccentric, right? It's so close to circular you wouldn't even notice. At least not from looking from a distance. All right? And because of that, I'm going to make the radius of Mars bigger than that, so it's out of our way. So I'll make it 360. All right? Okay, so orbital radius of Earth is equal to, now it seems to me, isn't it cosine of orbit angle Earth times Earth 1's radius plus, cosine of that times Earth 1 plus sine of times Earth 2. So this is like my quick and dirty hack. So demonstrate an exaggerated elliptical orbit for Earth. Demonstrate an exaggerated elliptical orbit for Earth aligned to the origin. That's the weird thing, right? Because of course, if you have an elliptical orbit, right? Who says it's like only this way? What if it's like this way, right? There's no law that says it has to be like, so obviously I'm just making this up. That's the problem, right? So I'm just doing this quick hack. But so if you look it up, NASA has all these orbital numbers. They give you the equations, so you can actually get this stuff live from a database, throw it into your code, and compute it from there. It's really cool, but it's huge amounts of work. I'm missing a close paren here. Okay, and we run. Earth 2 cannot be resolved. Oh, I said 0 and 1, excuse me. So Earth 0, Earth 1, go. Okay, so you see the Earth gets a lot further out in its orbit in the Y. And then, oh my God. I think we spiraled to the sun. I think I screwed up a little bit. Okay, obviously that wasn't right. All right, so so much for winging it on the elliptical math. Okay, so clearly cosine times this plus sine times that. I don't know why, but sometimes it must be 0 because how is that possible? R cosine theta plus R sine. if it was r cosine theta, r sine theta, that's the coordinates of it. But what I'm saying is that it's r. I don't know. Sorry, you can look that up and find out. Like, tell me. Come back to me with an answer, and we can do it. I'm not that wrong. I'm just the equation's obviously wrong, but it's not going to be that different. Sorry. Save it out. You can do it, or you can, like I said, if you want help, I'll help you look it up. But what would it be? Wikipedia. No, I should just Google it. ChatGPT would be even better. Equation of elliptical orbit given major and minor. Yeah, they're giving you the equation of the ellipse, which is really not a lot of fun. So I can see already, even though I guess I could click here, but let's see if it's x squared a2, or x squared over a2. Yeah, I was right down here at the bottom, right? So the equation of the ellipse is x squared over a squared plus y squared over b squared equal 1. So we have to like multiply them out to the other right side, so we get like some big constant, not 1. Solve for... That's the problem. Like at any point when I'm in a radius, I want to know when I'm at a particular angle. I just want to know how far out to go. Well, so I'll think about it, right? But it's a parametric equation of an ellipse. Oh, yeah, maybe I could search that way. Parametric equation of ellipse. X equal a cosine t, y equals b sine t. Oh, wait a minute, wait. If it's x and y, right, then I need to take the square root of x squared plus y squared to give you the length. All right, so it's probably not the most efficient thing in the world, but here, there we go. How about float x earth equals that? Y earth equals that. Orbital radius for the earth is equal to x earth times x earth plus y earth times y earth, and I guess we need square root of that, right? Alright, let's see if I do any better this time. That should be better. Okay, so it's getting further away in the y, and it's going up to there. So that's 300 units away, and Mars is still going further, I think. And now it should be 200 away here. Yeah. And now it should be 300 away here. Okay, so I got you a hacked up. I got what you want, but it took me a little while. There we go. Any other questions? Oh my God. So now, if you wanted to do this in OpenGL, yeah, we're gonna just we it's already 7:45. We're totally ready to do this. It's just a question of we're not going to do it in class now in code. I'll just show you the outline, and if you want to do it, you're welcome to do it. So keep this file, save as. So this is going to be S10. 3D solar system. Okay, so obviously what I recommend is if you're going to write a solar system, you don't want to keep on replicating all these variables, right? So you really want to write an object-oriented program, but that's beyond the scope of this workshop, right? But what I would recommend is, if you were doing this, that you would write a class called a body. So it should have location, size, the image, the axis of rotation, speeds of orbit, rotation, etc. Right? If you want to do elliptical. Right? Now, so everybody can do this. The only problem is that some bodies, I mean, we're just basically making something that goes around something else. There's no gravity here. There's no, like, physics. We're just making... So if you try to make the moon, you have to make the moon not go around the sun. You have to make the moon go around the Earth. So how would you do that? So I'm not writing this code for you. This is way, way, way beyond the scope because I don't know... A lot of you don't know Java, so you know... You would have to do this in either C++ or Java, right? You know, write something. It's going to be a fairly large object-oriented job. It's not impossible, but all right. So we're going to do it the brute force way, just as a demo of the math, and then anybody who's interested, we can do it if you're interested. But I'll do that out of the workshop with anybody who wants to do it. Presumably, you'll already know some Java if you want to do it in here. So let's see, background, translate. Okay, so if you're going to do a solar system, right? Then it's P shape, and again, I would put a P shape inside my body and have like each body knows how to draw itself. But right now, I'll just say P shape, sun, Earth, Moon, Mars, right? I am not doing all these. I'm just demoing. So sorry, this is not going to work, right? That's where I draw the line. We're not. If you want to do it, you're going to have to make it happen, and I'll support you. So we're going 3D instead of just 2D. We no longer care about rect mode. Okay, but now we do care about sun equals create shape, sphere, whatever size you want it to be. I suppose we should say no stroke. Yeah, so turn off the edges. All right, so if you want to do all these, we're going to have to get you the pictures, and I forgot to do that. But again, if anybody wants to do this, just come to me, and I will get you those damn pictures. I mean, I've got a whole directory on Google with like a huge amount. No, not on Google anymore. Now it's in Microsoft, whatever they call it, as we moved. Sun equals create shape. So we need to attach the sun.setTexture and its load image of sun.jpg. So obviously that implies I've got to get that thing. We've got to do that. And then you would do the same thing for Earth, Mars. So I'm not going to do these infinitely. I'll just do Earth, Earth. All right. But you see how repetitive this is, and that's why I say what you really want is to define it once in body, and then just say load the bodies from a file, and you just like read it up, and you can make a programmable solar system. I have wanted to do this for so long, and I just never had the energy to deal with it. Okay, so there we go. So I'm just going to like say moon. Oops. I'm going to give you I'm not going to do the texture, but moon equals create shape, sphere, or we could even get really cute and make the moon a cylinder. Okay, I guess Earth should be smaller than the sun, even in our little cartoon world. All right. Oh, it's not working with cylinder? All right, I'll make it. Right. No. I'll just make it a sphere. Why get cute? But I know there is. It does support other shapes. Anyway, all right. So there we are. So the difference now is the sun. The Earth is going around the sun, and you could just like take it from the other code that I wrote. You could understand that Mars is totally independent of Earth and use push matrix, pop matrix, right? So if you were trying to do this, you wouldn't do fill. Instead, you would just say shape sun and draw the sun, right? So that's all there is to that, right? Okay, but when you're trying to draw the Earth, you would do a push matrix, because wherever Earth is, that has nothing to do with where the other planets are. So you'd push matrix, you do whatever it is you want to do, and now it would not be rotated anymore. Now it has to be like rotate in the Y or the X, or you have to define which rotation you want. So it's going to get more complex. I'm just going to do it all in the Y. I think that's, it's going to be like this. It's going to spin in the plane of, so it'll be coming out at you. If you wanted it facing you, if you want to look down in the solar system, then it would be in the Z. So you could pick your poison, right? Whatever you want it to look like. Anyway, I'm just going to do Y so it kind of appears to jump out at you. We are not going to draw a rectangle. So we're going to say shape, Earth, pop matrix. Okay, so all the math is basically saying, now, okay, you could get a little bit fancier about your rotate. So your rotation, the plane of the solar system is like this, right? We're going around in a circle like this. And what we're saying is that the Earth is spinning in that plane, which is not true. The Earth is tilted 23.5 degrees off the plane of the ecliptic. And in fact, if you look, there isn't really a plane of the ecliptic, right? I mean, most of the planets are kind of sort of in a plane, but not exactly. I mean, it's not perfect. There's no law of nature that says that a solar system has to be 2D, and it isn't. We're going like this, and every now and then there's something that comes crashing in like that, that's going like this. So this, in fact, is one of the dangers, right? We don't know if there's some huge asteroid or something that's got our name on it somewhere way up there. We look around in our plane, but we don't tend to look out of the plane. So if there's one coming for us, we wouldn't notice it. It'll be a few decades, I think, before we start really surveying a sphere around ourselves. We just don't have enough telescopes yet. All right, so rotate Y, translate, rotate Y. Okay, so the rotate Earth, if you want to rotate, you need to get your axis, you need to now tilt your axis. So you could rotate around the X or the Z, it doesn't matter. It's kind of arbitrary. So I'm just going to, wait a minute. No, wait a second. X is here. Y is here. Yeah, so if I rotate in the X, I'm tilting it either toward me or away from me. That's fine. No, wait a minute. I don't want it to process. Just a second. Okay, so yeah, okay, sorry. You rotate to get to the right place in your orbit. You move there. You unrotate. So you are not rotated. Your y-axis is still directly up and down. That's why this works. So now you could say rotate in the X by 23.5 degrees times radians. That's times pi over 180. All right. So what you basically want is every body is going to have an axis of rotation, and you want to throw that in there too. Now, this is not quite right, because of course, if we're at 23.5 degrees and Jupiter's at 5 degrees, who says that they're like in the same direction, right? They could be like off there. So you need, if you want to really do this right, you do need a few more parameters. This is just sort of right. But anyway, this will get you the Earth looking like you want it to look. All right. And now, so here's the deal. Every planet would be surrounded by push matrix, pop matrix, so it doesn't apply those. But if you want moons, then you nest the moons in here. So what you would say is push matrix, you would do the moon there, and pop matrix. Okay, so it took a lot longer than I thought, but I'm not, like I said, I'm not going to really demo this. You could easily get this, just like load in a couple of pictures, and you should be able to get this going right away. But if you have the ambition to do this, I mean, I'll support you. I think it's a great thing to do.